This video is a review of Lancelot and the Ladder problem that we did in class in fall of 2019. I didn't like how the question was worded per se, so I just wanted to go through it again in case you missed any of the finer details behind the problem. So the general idea was that Knight Lancelot was using a ladder to get over the Camelot wall. And when we come to the problem, Lancelot is a third of the way up the ladder, and the question initially asks for this kind of weird force, and they draw it on the picture like this. And they have the letter R next to it. This is just what's called the reactive force. It's not a force that we typically use. And because the other way to describe it is this is the sum of all of the forces acting on the ladder from the ground. So if we take R as your hypotenuse force, well, there are two things that the ground does to support the ladder. And the first, we probably all know, is the normal force. And that's going to be the perpendicular component of this R value force. And then the other force is friction. And so these two forces are working together to create what's called the reactive force to the ground. And these are at a right angle to each other. And so they're going to have they are going to be the two pieces, the perpendicular and the parallel, for the whole ground force. And so this problem kind of asked it backwards, and they said find this R value first. And I think it's easier to start with finding what is the normal force first, then let's find the friction force. And then once we know these two sides, we can use the Pythagorean theorem in order to find what this R value is. Okay, so let's do the normal force first. Because this setup is in translational equilibrium, that means the sum of our forces in the y direction has to be equal to 0. Well, what forces are in the y direction? Well, we've got the normal force, of course, that we're interested in. We also have the weight of Lancelot. So this is going to be the weight of Lancelot. Okay. Then we also have the weight of the ladder itself. We're not going to assume this ladder is massless. That's a silly assumption to make in this case. We know the ladder has some sort of mass. I'm going to use a lowercase l for the ladder. So uppercase L is Lancelot, lowercase l is the ladder. Now, I accidentally put a plus sign here, but we know that these two weight forces are actually going to be in the opposite direction of the normal force, so we really should use a minus sign there. Okay, so from the normal force should be equal to the weight of Lancelot plus the weight of the ladder. Okay, now the problem that, in the big wordy problem that they gave us, they told us the weight of Lancelot was 800 newtons, and they told us that the weight of the ladder was 180 newtons. So these are already in newtons, we don't have to convert, and so that means the normal force is just 980 newtons. Okay, so when we have this equals 980 newtons. We already have one side. That's great. Okay. For the other piece of translational equilibrium, we have to say that the sum of the forces in the x direction also equals 0. Okay, well, what forces are in the x direction? Well, we know that there's this friction force between the ground and the ladder. So we've got this friction force. And then the other piece of information that they showed us in the picture was that there's a force from the wall here. They just called that F. So this is the force of the wall pushing against the ladder. The ladder pushes against the wall, so the wall is going to push back on the ladder. One thing of note, there is no friction on this wall. that's just to make the problem a little easier. They did say that there's friction here, but we just want to look at just at this force on this wall. Okay, so that of course is in the x direction, so we will add that, and it's acting in the opposite direction as our friction. So we know that the force of friction is equal to the force of the wall on the ladder. Well, that's great, but one problem, they didn't tell us in the problem what this force value actually is. Okay, so we have two unknowns and one equation. So how do we rectify this? Well, if we have two unknowns, we need at least two equations. And so we've done this with translational equilibrium, but if we assign a pivot point on our ladder, we can also look at rotational equilibrium. Now, there was no pivot point given to us in this problem, so it might not be straightforward that we have to use rotational equilibrium. But if we think about the ladder as a pole that can rotate, for example, if it was to slip off the wall, it would rotate down. Then rotational equilibrium becomes a very simple addition to this. The one tricky part is they did not tell us a pivot point. And in reality, the pivot point can be anywhere. It can be right in the center, it could be where Lancelot is standing, it could be at the two ends. But I want to give a suggestion, and my suggestion is that we find a pivot point at one of these two forces. By putting the pivot point at that force, when we calculate the torque as the radius from the pivot times that force, the radius is 0, and so that force is giving you no torque. So if by selecting one of these two forces to place the pivot point, it allows us to essentially remove one of the variables from the equation. So I'm going to recommend that we use the pivot point on the ground. Okay, you could do it up here, that's absolutely fine, but I think it's a little bit more interesting to put it on the ground. So we're going to start there. So we need this rotational equilibrium. Rotational equilibrium means the sum of our torques is equal to 0. And so we have to look at which forces are causing a torque on our ladder. So from the pivot point, we know that the normal force and the friction force both are acting for this grand total force of R for the ground. So all of this we can ignore because they're 0 meters from the pivot point. Then we've got Lancelot. Well, his weight is going to cause a torque. The ladder itself is going to cause a torque. And then we've got the force up here, which is going to provide a torque as well. So we've got torque of the ladder, we've got torque of Lancelot, torque of the ladder, and then the torque of this force here. Now we have to know that these equal 0, so these can't all be positive forces or positive torques. So when we go and write out our RFs, some of them will have to be negative. So the torque of Lancelot is going to be the radius of Lancelot times the force of Lancelot. But we have to be careful here because the force of Lancelot is not perpendicular to the ladder that we're using as our rotational device. So I'm going to draw that a little bit bigger down here so you can see it. So we've got Lancelot hanging out a third of the way up the ladder, and we know that his weight is 800 newtons. That get 800 newtons, okay? So this is not perpendicular to our ladder. So this is just an inclined plane, so we're going to go back to how we draw our inclined plane with our perpendicular and our parallel components. And remember, the angle of our incline is also the angle we place up here. So we want the perpendicular force here. That's going to be cosine. So we're going to use 800 newtons times cosine of theta as our force. So when we go to write that in variable terms, we're going to take the force of Lancelot times cosine of theta. Now, is this causing a clockwise or counterclockwise torque? Well, we look at how this would do with the ladder. If this was the only force on the ladder, it would pull it this way. That's going to be the clockwise motion. So that, of course, is going to be a negative torque. We're going to do the same thing for the ladder. Now, the ladder is providing a torque, and when we have a pole of uniform density, we place the radius in the center of the pole. They tell us the weight of the ladder is 180 newtons. We're going to repeat that step just like we did with Lancelot. We have the theta here, so this is going to be 180 newtons times cosine of theta. Okay. So we've got the radius of the ladder, the force of the ladder, cosine theta. Once again, it's providing a clockwise torque, so that's going to be negative. The last piece is the torque of the force at the top. So the torque of the force at the top, we can draw it like this. So this is our force. But notice, once again, it's not perpendicular to our ladder, but it is parallel to the ground. So when we have our theta down here, that's going to be the same theta as up here. So when we draw a line directly down so that it is perpendicular with our ladder, we see that that is just the sine of this force. So we're going to end up with the radius of this force times the force times sine of that angle. Now this is going to provide a counterclockwise torque. Notice how it's sort of this perpendicular piece is in the opposite direction of our two weights. So that's going to be counterclockwise. That's a positive torque. Now all three of these pieces have to equal 0. Okay, so what I'd like for you to do is pause the video and see if you can calculate for F in terms of all of these other variables. Okay, so pause the video, try it. When you replay the video, I'll have the answer for you. Okay, so solving for the force, because all of this equals 0, these two just go to the other side. And then we're going to divide by the radius of the force times sine of theta. Okay. Now, I haven't been using numbers too awfully a lot in here, but we have the weight of Lancelot, we have the weight of the ladder. What they tell us is the radius of the entire ladder is 5 meters. Okay. And so they tell you Lancelot is 5/3 of the ladder. Sorry, his radius is going to be 5/3 because it's 5 meters and he's a third of the way up. The radius of the ladder, because we put the center of mass right in the middle, that's halfway there, so 5/2. And the radius of the force is the entire 5 meters to the top. The other piece of information you're going to need to find this force is the angle. The problem gave us 53.1 degrees, kind of odd, but that's what they gave us for the force, or for this symbol here. So what I'd like for you to do next, of course, pause the video, plug in your numbers, and get a value for the force. Okay, so you should have gotten 264 newtons for that force. Okay, so we've done all of this work. What does this mean? Well, let's backtrack. What did we just do? We just found the force that the wall exerts on the ladder. Well, then let's go back up. We just said that the force from the wall is equal to the force of friction. If we work our way back up, we've got 980 newtons for the normal force. So this force of friction, because it's equal to the force of the ladder, should be 264 newtons. So I leave the rest of this problem to you, the listener. You've got two sides of a triangle. Can you find the hypotenuse? And your new angle here. That will give you the final answer for what force does the ground exert on the ladder.